In this lecture, we will discuss how to estimate the unknown parameters of our models, discussing first the least squares estimator and then the weighted least squares estimator. We begin by looking at our assumption. We are assuming that we have a linear model where the unknown parameters that are stored in theta are multiplied by some regressor matrix x, which is then multiplied its conjugate transpose as usual there. We assume that x, the regressor, is a known vector, whereas theta has n theta dimensions, and this is what we want to estimate. So for an example, here is a process which is nonlinear in z, but it is linear in the unknown parameters, a1, a2, and so forth. And this is the important part. It's that the unknown parameters are the data is depending linearly on the unknown parameters. So let's assume we have n samples. We gather up the samples in a vector y, the regressor matrix we stack together to a matrix x, and then the noise into a matrix e, to vector e. Then we can write our n observations like y is equal to x theta plus e. The least squares estimator is the one that minimizes the distance between the vector y and what can be described by our model. What can be described by our model is the combination of the columns in x multiplied by theta, like this. So this is a vector, and we rotate it based on the choice of the vectors theta, and we try to find the vector parameter theta such that the distance between y and x theta are minimized. And this argument, this theta, that minimizes this cost function, the cost function here being the norm, is the one we select as our least squares estimate. And this is just a notation wise, it's a 2 norm, so it's an inner product of the vector A with itself. Now, if I rewrite this expression like this, so first of all I will write out the 2 norm, and then I'll make a little nifty rewrite such that I write it like this. This is not an obvious rewrite, but if you multiply it all together, you can see that it is true. Here, the x dagger is the pseudo-inverse, whereas pi x is the projection matrix onto the space spanned by the matrix x. The reason why we rewrite it like this is that you can notice now that these parts of the minimization does not depend on theta in any way, so they are irrelevant for our minimization. Furthermore, we can see in the first part here is that the best way of selecting theta would be to select theta such that this part turns to 0. So therefore, if I select theta as x dagger y, this part will be 0, and I will clearly minimize the expression. So therefore, our least squares estimate should be found as x dagger y, where x dagger was the pseudo-inverse of the matrix x. The pi x here, as I noted, is the projection matrix. That is what you get if you project the vector y onto the space spanned by x. If I look at this geometrically, the vector y can be seen as consisting of 2 components. The part that is in the range space of x, that is the space spanned by the columns of x, as well as the component that does not lie in the range space of x. Here, the range space is the space, all the points that I can reach by the combination of the columns of x. So for instance, if I have x consisting of 2 columns, x1 and x2, any point that I can reach by having a complex number c1 times x1 plus c2, another complex number, times x2, will be in the range space. So that is all the reachable points as due to a linear combination of these 2 vectors x1 and x2. Any other point, those are the points that lies orthogonal to the range space. Those are in the so-called left null space. Any vector in the left null space will be such that those points are unreachable by a linear combination of the columns of x. So we note that the vector y, which is n-dimensional, consists of 2 components. One that is in x, which has dimension n theta, because there's n theta different columns in x, and one component which lies in the orthogonal space, which then has n minus n theta dimensions. So the component p, which lies in the space, can be written as a linear combination of the columns x multiplied by the unknown parameters x, by the estimated parameters theta. So since the estimated parameters can be written as x dagger y, I can rewrite it as a projection matrix onto y. So p, the point in the range space, can be seen as the projection of the vector y onto the range space of y. The error, on the other hand, that is the difference between y and p. That will be orthogonal to the range space of x, and as you can see this geometrically, since y consists of the components e tilde here and p. E tilde then must of course be orthogonal to p. So e tilde will be y minus x theta hat. So that is the projection onto the space orthogonal to x. That is the projection onto the left null space of x. If I would like to estimate the variance of this error, I can therefore compute the e vector and simply divide by the number of dimensions in the vector. So there will be n minus n theta dimensions, since the range space of x contains n dimensions. Simply, it's the projection onto the space orthogonal to x divided by the number of dimensions in this space. If my noise is normally distributed, then the estimator will be unbiased, meaning that the mean of the estimator will become the true mean. Furthermore, I can show that the variance of my estimate can be written like this. A nice feature of the least squares estimator is that it is the best linear unbiased estimator, the so-called blue estimate. That is to say that there is no other linear unbiased estimator which has lower variance. So basically you are saying this is the best possible thing you can do if you are restricting yourself to having a linear and unbiased estimator. Here's an example. This is the ARP process that we have been looking at before. I can rewrite the ARP process like this, where this would be my regressor and this would be my unknown parameters. Notice that this will look slightly different, since in the earlier case I was looking at when I had y is equal to x t theta plus e. Here I have the x on the other side, so basically there is a minus sign that I need to move into theta. If I stack them up my n samples, I will get the same expression as before, but then with this minus sign due to this effect. Interesting to note here is that the vectors now must start at p plus 1. The reason for that is that I will have in there y of t minus p. So if I will use components earlier than p plus 1, they will be of t equal to 0 and t equal to minus 1 and so forth, data that I do not have. So I need to stack up my estimate to only contain the values that I actually have. That's why I need to start at p plus 1. Okay, so what happens if the additive noise has a color? That is, that the covariance matrix is not an identity matrix. So here let's assume that the covariance matrix is Re, and I will then compute a matrix square root of this matrix inverse. So that is the same thing as saying that Re inverse can be written as W star W. That is, then W is a matrix square root of Re inverse. The way you form the weighted least squares is that you minimize the weighted distance between y and x theta, where the weighting will be then this covariance matrix. So a weighted norm like this will look like this, meaning that I will weight the components of the norm with the matrix inverse. Basically, you're saying that I will trust the different components differently, such that if they have a large variance, I will trust them little, but if they have a small variance, I will trust them more. Right, so how do you deal with this? Well, the first thing you do is that you rewrite it out, so I have the expression. Then I create two new variables, y tilde, x tilde, and an e tilde, of course, and rewrite the minimization using this expression. Then it turns to this. And what you can see there is that this is exactly the least squares estimator. So I can rewrite my estimate, the weighted least squares estimator, and it will look exactly like this. Then what I do is I reinsert my y tilde and x tilde, and I get the expression for the weighted least squares estimator. And similarly, I can find the variance of the weighted least squares estimator like this. This is going to be the best possible linear unbiased estimator if the noise has the covariance matrix Re.